In the 1880s, two of the greatest inventors in history fought one of the most consequential technological battles ever waged. Nikola Tesla championed alternating current, or AC. Thomas Edison championed direct current, or DC. This disagreement is well known as the War of the Currents, and it wasn't just a business rivalry. It was a fundamental debate about whether the future architecture of the global system, what it would include. So this included how electricity was generated, transmitted, and delivered to every home, every factory, and every city on Earth. And Nikola Tesla won this battle. And in the world we live in today, every wall outlet, every power line, every transformer on every telephone pole is the world that Tesla helped build. I've always admired Tesla deeply, not just for his brilliance, but his tenacity. He pursued a vision and with an intensity that most people couldn't even imagine or sustain. And what drove him was not profit or fame. It was a genuine desire to help humanity through science and technology. And this is the spirit that this channel is built on. In this video, I'm going to tell you about the full story of AC versus DC, the physics, the history, and the battle, and why this 130-year-old debate is more relevant today than ever, because the future of clean energy is actually bringing DC back in ways that Tesla never imagined. My name is Dr. Colleen Spiegel, and this is the Tesla Institute. So before we get into the battle that was waged, let me make sure you understand what exactly alternating current and direct current actually are, because the physics is what determined the outcome of the War of the Currents. So direct current, or DC, flows in one direction only. The electrons move from a negative terminal of a power source through the circuit back to the positive terminal. It's always constant, always steady, one way, always. So if you plot DC voltage against time on a graph, you'll get a flat horizontal line. The voltage does not change. It's constant at whatever the source provides. So if you have a AA battery with 1.5 volts, that's your voltage. 12 volts from a car battery, that's going to be your voltage, or a certain voltage from a fuel cell stack or solar cell panel, that'll be your voltage. So a battery produces direct current. A fuel cell produces direct current. Solar panel produces direct current. All these devices, the chemical or photovoltaic process that generates the electricity, drives the electrons in one constant, consistent direction. Alternating current, or AC, is fundamentally different. Instead of flowing in one direction, AC reverses the direction periodically. So if you plot AC voltage against time, you don't get a flat line like direct current. You get a sinusoidal wave. So this is a smooth curve that rises to a positive peak, falls back through zero, continues to a negative peak, and then rises back to zero again. This cycle repeats itself continuously. So in the United States, the household current completes this cycle at 60 times per second, so it's 60 hertz. In most of the rest of the world, this cycle occurs at 50 cycles per second, so 50 hertz. So the peak voltage of US household current is about 170 volts, but because the voltage is constantly rising and falling, it actually spends a lot of time near zero, and the effective voltage that does the useful work is lower than the peak. And this is called RMS voltage. Root means square. The households in the United States, it's 120 volts. So this was the number you see on your appliances and outlets. In Europe, the RMS voltage is 230 volts. So here's a useful way to picture the difference between AC and DC. DC is like water flowing steadily through a pipe in one direction continuously. The pressure is constant, the flow is constant, and it's predictable. It's the exact same flow rate. AC, the water in the pipe is being pushed back and forth by a crank connected to a piston. It's like the water sloshing rapidly at 50 or 60 cycles per second. The water never actually travels from one end of the pipe to the other. It just oscillates back and forth very rapidly. So the pressure alternates between positive and negative with each piston stroke. So that back and forth motion sounds really inefficient. So why did Tesla champion AC over DC? The answer lies in transformers. And the physics of how transformers work is the key to understanding the War of the Currents. A transformer consists of two coils of wire called the primary and secondary windings, and they're wrapped around a shared iron core. So when alternating current flows through the primary winding, it creates a constantly changing magnetic field and induces a voltage in the secondary winding. And the ratio of the voltage induced depends on the ratio of the number of actual turns in each coil. So if the secondary winding has 10 times as many turns as the primary, the output voltage is actually 10 times higher than the input voltage. This is called a step-up transformer. If the secondary winding has 1/10 of the turns, the output voltage is 1/10 of the input. This is called a step-down transformer, and this only works with alternating current. A transformer requires a constantly changing magnetic field to induce the voltage in the secondary coil. So DC produces a static magnetic field, which induces no voltage in the secondary. So it can't be transformed efficiently with a simple electromagnetic induction. So this is the fundamental principle that determined the war of the currents. And this is why transformers matter so much for power transmission. Electrical power is the product of voltage and current. Power equals V times I, voltage times current. So if you double the voltage and keep the power the same, the current must halve. If you increase the voltage by a factor of 100, the current drops by a factor of 100. So this is the critical part. The energy lost as heat transmission wire depends on the resistance of the wire and the square of the current flowing through it. So this is Ohm's law, or V equals IR, applied to power dissipation. Power lost equals current squared times resistance. So if you reduce the current by a factor of 100, you reduce the transmission losses by a factor of 10,000. So 10,000 times less energy wasted as heat in the wires. And this is why AC transmission is so efficient. The step-up voltage up to hundreds of thousands of volts before transmission, the current drops to a tiny fraction of what it would be at a lower voltage, and the transmission losses become almost negligible, even over hundreds of miles. So AC can be stepped up to very high voltages, like 115,000 to 765,000 volts for long distance transmission. And then it can be stepped back down to safe levels, like 120 or 240 volts, depending on where you live, at the destination. So DC in Tesla's era could not be efficiently transformed. You could not easily step up DC voltage or up or down, which meant that DC power had to be transmitted at the voltage it would be used at. And so the losses during transmission were actually catastrophic over even small distances. So Edison's DC system required a power station every mile or so to overcome these losses. So this was acceptable for a dense city like Manhattan in New York, where a place like Pearl Street Station could serve customers within a small radius. But it was not practical for transmitting power across, like, let's say, a state, a country, or even a continent. So Nikola Tesla understood this. Westinghouse understood this, and the physics made the outcome of the war of the currents almost inevitable, even before a single demonstration was staged.